Probably should start. Hi everybody, good afternoon. Today I'm going to talk about the efforts we are doing here to improve the quality of the XBT measurement inside the probe, in the production line, more in the manufacturing point. So we did a lot of experiments here in the sea trials, and I'm going to talk about that here. And this is in collaboration with the Lockheed Martin SIPCAN. Some of the engineers there, they're helping us design the experiment and also the analysis of the. So how do I need to click, right? So this work is also part of the XBT network. So the XBT network is a global network of now American chips that deploy the probes along fixed transect lines, and used to be in a global sense to measure temperature in a global scale, and now we are fixed to transect line. And just to have an idea, we drop around a global every year 24,000 XBTs, and 8,000 of them is here from AOML. Now we only focus more on the things such as AMOC variability, global currents, ocean heat content, and even for data simulation for temperature profiles. So the XBT is one of the longest observational records we have in the ocean for a temperature, both in a global scale and also along the transects. And it was initially designed just for Navy applications to detect the temperature gradients and sound speed in the water. But then over time we apply more on scientific studies as well as climate, where we need a better accuracy. And XBTs, the data and was found in comparison to CTD and BOTO over the history, and found to be generally biased, have a positive bias of 0.2 to 0.4 degrees Celsius over time, and a lot of effort has been deserved to that to correct the data over the historical record. And a lot of studies here, as we can see, a lot of them deserve time, and they apply different corrections. And nowadays we even correct like for the time variability as well as depth and the temperature offsets that we generally see. And they generally rely on CTD and XBT, the side-by-side comparison. This will be the focus of this study as well. And nowadays most of the probes here we apply are either T7 or Deep Blue probes. So Deep Blue is most of the deployments here are from Deep Blue probes. And yeah, one of the questions we want to address is how we can improve this data, not only in the processing like it has been done over a long time, but also in the production line, and what SIPCAN could improve in the manufacturing side of the production. So one of the study we had is on to correct the depth is actually include the pressure switches. So we could put one or two would be, as our study showed, the best one to correct the depth bias. So in a regular depth bias, we use two pressure switches, and we can correct really well the depth bias. However, this is not that can't be produced right now, and there's a lot of manufacturing constraints that it doesn't allow to do it now. So what the main objective of this study here is also on the temperature side, not on the depth side, but with implication as well. So we have these sea trials that we performed together with the Lockheed Martin, where we deploy XBT and CTD at the same time. And we trace the improvements in the accuracy of temperature and also, as an implication of depth estimates, by little changes in calibration and probe improvements as well. So this study would give a recommendation for new improvement in the XBT over time. So a little bit of the outline. I'm going to talk briefly about the XBT system and the cruise that we performed here at the UML, and the main result of a few topics on the side-by-side comparison and the proven corrections that we performed, and a conclusion and possibly future work implications. So the XBT system is a system of all the way to the probe and to the record system and computer, and all the way to transmission that could be transmitted to real-time satellite. So it consists of a hand launcher or the auto launcher that drops the probe in the water, and it goes to an interface box and the data acquisition system that transforms that resistance or voltage signal into temperature. And so the XBT probe has one thermistor inside that is sensitive to temperature. And yeah, so that's the whole system. And the way XBT measure depth and temperature in the water, that depth is estimated using a flow rate equation that is proportional to time, and time squared, the time of descent of the probe, and A and B, A is related to most the terminal velocity of the probe in the water, and B accounts for weight loss and wire derailing, and the wire is inside the probe, and as it expands over time with the depth, it changes its mass. And the temperature is measured with the thermistor, is inside the probe nose, so the water passes through a hole in the probe nose and pass over the thermistor, and that records a resistance that we turn into a temperature record. So the typical errors that we find over time, so nowadays people correct for many more of environmental characteristics, but the three main biases that find is related to the temperature accuracy, that is stated as 0.1 Celsius. This is the maximum tolerance or let's say the total accuracy. In terms of one standard deviation would be about 1.2 Celsius. And this is due to, for example, a calibrated thermistor or wire resistance. And the record device, nowadays it's moved from the analog to digital, and that improved a lot. And the depth offset, that is about 5 meters. And this is due to wave height variability, entry velocity, and angle of the probe. So it's things that happen at the surface generally. And also depth linear barrier, that's over the depth, that is the flow rate equation error. That is due to like environmental property as well as the probe mass and the wire mass and wire density and things like that. So one of the questions that we want to address here is how to constrain the thermistor variability, the thermistor to thermistor variability, and also the probe mass will influence the temperature and depth errors. So we performed some side-by-side comparisons. We have data that we collect during 3 cruises. First, the Western Boundary Current time series in 2012, and also 2 P&E cruises that are more or less in the same line here. One in 2013. There were two cruises in 2013. This from the second cruise, and this is the P&E in 2015. And just a little bit on the details of each of the cruise. The Western Boundary series deployed 42 XBTs, and within two different probes. One is standard, that is standard deep blue, and the experimental that we constrain the physical properties of the thermistor to see if we change the accuracy of the thermistor. And so the PNE 2013B that we deploy almost 100 XBTs, this is the most comprehensive that I'm going to show here, that we deploy 3 different probes, as the 2 already talked about, and a tight weight tolerance that we reduce the variability of the mass of the probe. And I'll talk a little bit about more of each probe itself and what it can improve in the data. And also we applied 3 corrections, one for wire imbalance of the resistance balance in the wire, the thermistor calibration in factor in a fixed bath, and a thermal time constant, that is the time that the thermistor take to record a step in the temperature. And in the third cruise, the 2015, we deployed 44 XBTs. Just one type is we call enhanced XBT. That is basically the tight weight tolerance, and that we apply the thermistor calibration that you will see that is the best one that performs over our experiments. So I want to talk a little bit about the probes that I just introduced. So the standard is the regular deep blue probe. The experimental is what's called the screen thermistor, so they get the thermistor with the physical property most equal, and then that will be less variation. So the thermistor would be inside the probe here. The tight weight tolerance that control both the head of the weight of the head and the wire spool inside the probe. And the enhanced XBT that is similar to the tight weight, so it constrains the weight of the probe and also apply a thermistor calibration. So a little bit on what's the weight tolerance of the probe. So the probe has 3 parts: the zinc nose, the wire spool inside the probe, and the afterbody, the black part of the probe. So most of the weight is, so the total weight is 730 grams, and the variability is about 5 grams. So this variability, some early study have said that the mass of this variability of the mass would change about the way it behaves in the water. And so it's just to show how it varies in our experiment, the tight weight tolerance probes. We reduce this variability to 2 grams in the wire weight, and the nose weight, it goes to 0.2 grams. So we reduce the total variability from 5 grams to about half of it, and we'll see how it improves the temperature. So, and I talk about the probes now. I'm going to talk about the corrections. So one of the corrections we apply is for the wire imbalance. So the thermistor is linked to 2 wires inside the probe, and this is the canister, and there's a resistance here that balances the difference between the 2 wires. And then we measure that resistance and say, oh, is that resistance, if we include the information of that resistance, is that going to improve the temperature accuracy? Because if we read the resistance and transform that to temperature, if we put one offset of the resistance, that would create one offset in temperature as well. So in the thermistor characterization, we put the probe, they do in the manufacturer, so put the probe inside a water bath and tightly control that 15 degrees Celsius and see what the probe register and what would be the standard one. And that difference would generate also a bias in temperature. And the last is the correction is the time constant. So the time constant is the time required for the thermistor to detect 63% of a step signal, and is thought to be around 0.6 to 0.13 second. This is very little. It's about 1 meter. It's less than 1 meter in the water. So that would also produce a temperature bias because it will shift the whole temperature profile up. So just how more or less each correction behave after correcting the temperature, we see that both the wiring balance and the thermistor, they provide one offset in temperature, and the time constant, it just shifts. So we see just the shifted profile. When calculate the difference, we see that where the gradients are stronger, we have the most difference here. So another part of the methodology is how to detect the errors, the temperature offset, the depth offset, and the depth linear bias. So for that, we rely on the CTD data to tell us like what the true temperature is, and then we calculate depth gradients over the depth, and then you see the red and the green here. So the increase over depth, and then we just shift to the temperature profile, and that with that we eliminate the depth profile, and then you can calculate a true or pure temperature offset here instead of the one that are related to the bias. And also the temperature is a linear relationship with the depth errors. So also on the CTD and XBT comparison, we see that there's so we take a CTD as the ground truth, but you see in a real cruise where you have the CTD going up and down, we can have a shift here, kind of a hysteresis behavior here in the CTD, depending on if you go up and down. And in this case, the XBT is right in the middle here. So, and this could give even different offsets here. So we decide to get the downcast of the CTD, because is where the sensor is located on the bottom. And and we eliminate all the XBT profiles that are dubious. This is a classic leakage, right? So I go to the results. So I start with the Western boundary time series. So again, this is two probe types, the stranded and the experiment. So we're going to show how constraining the thermistor would improve the temperature accuracy. So we have 42, each one, like both have 21 different experiments. And for the experimental probes, we see that just for constraining the thermistor, we reduce in half the temperature bias in this population. Of course, we have just 20 samples. It's not very statistically significant. We can see clearly a shift toward lower biases in the screen, the thermistor. So and then we go to a more complex experiment where we deploy, of course, the PNE 2013. We deploy the 3 different probes and use 3 different corrections, post-processing corrections. So we see what each probe could do and what each correction would do as well with the data, and if we can reduce any of the bias, and if is anything that is significant on that. So this is one of the main results here. So this is the temperature offset. So these are all the probes, all the standard, the tolerant weight, and the experimental probes. So this constrained the thermistor, and this constrained the mass of the probe. So we see that initially, and the black is the original errors, original temperature offset. First, you see that they are all positive offset. This is what several other works have shown, that there's generally a positive temperature offset, and when so we see by the different probes, just looking at this, we see that for example, the standard probes, we have a higher offset than the two other probes, and generally above 0.05 Celsius. And when you apply the wire imbalance, there's almost no change comparing the red with the black. So if we add that information about the wire resistance, it almost doesn't do anything. In terms of thermistor calibration, if you do the bath calibration of the thermistor exactly at 15 Celsius, we have a really strong reduction of the bias here for most of the type 8 probe and experimental probe. And interesting that in the standard probes, we actually have a reverse of the bias. And yeah, I'm going to talk about this later, but this could be about maybe we should not use only 1 point for the standard, but 2 or 3 points for the calibration. And the time constant didn't do anything, and when we add all at the end is just the thermistor calibration. So the thermistor calibration is really important to reduce this positive bias that you have in the XBT measurement. And in relation to the depth bias, or both the depth linear bias and the depth offset, this is when you apply original and all the calibrations. So we see that the calibrations don't do anything significant with the data, even though we in the thermal times constant, we just shifted the data, the temperature up, and that and we see that there's some variability, that generally the depth offset and the depth bias are generally opposite to the other. This may be part of the method of the calibration. If you fit a linear bias offset and a slope, that's generally, they are very well correlated. And this is just a summary of this experiment. So this is what this is for the temperature offset. So initially we see that the experimental and the tolerant weight, they have a little bit better performance than the standard probe. And when we apply all the corrections, and we see that this goes really close to zero, and close to the 0.02 that we put as our goal to improve the temperature accuracy of the probe. So, and then we see that that flipping of the side of the standard probe that is overcorrected, due probably to that 1 point instead of a linear relationship over depth. And yeah, in depth we see that there are not significant changes in all of the probes. We see that the tolerant weight is closer to zero in mean, but the variability is still pretty high. So we don't see the restricting the mass of the probe too much improvement in the depth offset and the depth linear bias. So because we have too many parameters here, we have all the treatments and all the probes. So a good way to look at that is just an analysis of variance. I'm sure the biologists, they study, they use that a lot in their colleges. So when you have, for example, different treatments and different populations, and it's basically fitting a linear regression to the data, where you have the mean is, I apply the mean here, the mean of the standard probe. So all the parameters, if they are different than zero, is that we are confident that this is a significant significant improvement over the standard population, just to a way to calculate the significance. And again, we see for the temperature offset, so for all the 3 probes and the 4 corrections, so we see that these in bold are the significantly different than 0. They are higher than the standard error, and the correction 1, correction 3 are not significantly changed. So we see again the reduction of the bias compared to the standard, and when you added the thermistor correction, we have also, so they're all significant, just to test the significance of the data. And one of the things that we may take into account is that the tolerant weight shouldn't be represent an improvement in the temperature itself, but only in depth, although it didn't represent too much in depth, but did in temperature. So one of the beliefs that the thermistors that were screened as well, even though they don't have that information, but there's some ideas that that's what may have happened here. And again, the depth biases, within the corrections, we don't have, of course, the corrections are not significant. And we see that there's some significance here, even though it's the experimental probe that has bigger bias than the other, and that may be just because of the population is not very big. So in the last cruise, we use this information from the PNE cruise, and we use the best correction, that is the thermistor calibration, and the best temperature, that was from the tight weight tolerance, and we put them together and did another cruise just with this probe, and just to see if we confirm the results that we already had. And just and this final comparison here, we see that of course the temperature, initial temperature before the calibration was still, the temperature offset was still really high, 0.1. That's what is generally what you find in standard probes. And after the calibration, we have a reduction in the temperature offset, and we believe that this thermistor, they were not screened. They just used the standard thermistor. So we have the calibration, did a good job in reducing, but we didn't have the improvement of the screen thermistor. So just the tight weight tolerance. So a real enhanced XBT probe should have both at the same time, the screen thermistor and the tight weight tolerance. So this could be more close to 0 here instead of just having a reduction by half here of the temperature offset. And again, just to test that they are significant when we do the calibration, the temperature offset there. And so I was a little puzzled why the tolerant weight didn't do any good job in reducing the temperature bias. But you see that calculating the fall rate coefficients A and B for all the probes in the first cruise and the second cruise, we see there's still a lot of variability compared to the standard, to the SIPCAN fall rate equation and the Hanauer one. Even though the means are similar, but there's still a lot of variability independent of the probe type. So the constraint of the mass here didn't do much in constraining this variability of the fall rate equation. So just a brief summary of all the numbers we got here. So in the experimental probe, we have a reduction of about half the bias, and this was performed just for the calibration without using experimental probes. And when you use experimental probes, and in this one here, we could reduce also to zero and really constrained to 0.02 the variability. And the bias, they are still in the tolerant weight probe. We have a reduction of the bias here, but it's still a strong variability. So we didn't get any extra information there. So just to conclude, the thermodynamic constant, which is with the shift of 0.13 seconds due to the resistance time of detection, that didn't do any changes. Some work as the Rezagheti et al. 2007, they estimate that as a much high as about 6 seconds, that would be up to 4 meters, this difference, to detect a step signal. So that could have a stronger effect on the biases if we apply that instead of just the standard manufacturing thermistor delay. So for the wire imbalance, so that if we include that information of the resistance to the resistance profile and then convert that to temperature, is also really small. But the thing is that this residue is less than 0.1 of the reading, 0.1% of the reading, so we wouldn't expect much there either. And about the thermistor calibration, which is the one that gave us strongest effect and strongest bioreduction, and even an opposite. So it got rid of that positive bias in the XBT that has been seen for a long time. We can even constrain to less than 0.04 Celsius and reduce strongly the bias in experimental probe if we use the thermistors that are more alike physically to the other. And in the case of the overcorrection of the standard probe, we see that, remember that plot that we see that the effect of changed the signal, but not too much the magnitude. And this is because also in Rezagheti et al. 2007, they see that maybe the calibration, so this is the bath temperature and this is the bias. So we see that that this could be a linear relationship over depth. So if you just use 15 Celsius, wouldn't be enough. But for the standard calibration, we need the whole profile. And in terms of the probes, we have the experimental probe that in addition to the thermistor calibration, we have a really good effect in reduction of temperature. The tolerant weight didn't show any effect, not considerable in the depth biases. So reducing the mass of the probe, at least in this experiment by half, didn't show too much effect. And for one enhanced XBT probe, that didn't use the screen thermistor, the battery thermistor. So we need to add that to have this enhanced XBT probe, and in the future the climate quality probe. And some of the effort, like the pressure switches, as I showed a little bit at the beginning, and Francis and Gustavo, they are also working on improving the parameterization of the flow rate equation. That are works that also together with this could help improve the accuracy of the probe. So that's it. Thank you. Nobody's left. Yes.
Yeah, two questions. One is, you didn't mention anything about the drop height. Is that a concern? And the second one is, what's the causes of your variability in your fall rate, your A and B changes, which you showed towards the end?
Right. So the first question, the drop height. So we try to constrain the drop height here. So all of them, they had 4.2 meters, I believe, the one we recorded. So that's the PNE 2013. And Yeah, this is part of the flow rate equation improvement that Francis is doing. So they're exactly doing experiments where they change the high variability and they add an extra parameter to the flow rate equation. And about the A and B, the two parameters in the flow rate equation. So the A is the terminal velocity of the XBT in the water. So that should be constrained, and also the wire derailing, the B parameter. The B parameter should be very dependent on the density of the wire. That's what a few works have said in before. So we constrained in the tight weight tolerance how this wire, so the density of the wire, but that didn't show too much effect on the variability. So we estimate that just a linear regression. We calculated the biases, the depth bias, and then do a linear regression. That's how we get these two coefficients.
So maybe in this, you had a plot there where you show
Yeah.
sort of factory, coefficients, and then I thought were the experimental. You get this one here.
Yeah.
So what's this? So you have the Sipacan value, which I guess is the factory provided value.
Yes.
And then you see a significant, difference, scatter.
Yes.
From there. So is that basically the difference? You think differences in wire tolerance, etc.?
That yeah, a few factors may affect that. One is the gradient method itself that is not perfect. So we are trying to fit a line, and sometimes we have the depth to residues that I like that. So we have to fit a line on that. So that and we see that the parameters are really really. So if you fix one parameter, you got the other one worse. So some people estimate that in a two-step, so they just get the offset. For example, when you have a thermostat in the water, that you don't have too much temperature variability. So they get the no, sorry. I'm talking about the temperature offset. So yeah, this there are other things that influence this, as the probe, not just the probe weight, but the probe, yeah, the shape of the probe and the
Environmental conditions as well?
yeah, that's what we find in this one. That seems to be really linked to even for the same probe we have a strong variability. So one of the things I want to check if is, maybe one is more close to the equator, the other. So I don't know if and also in the western boundary time series that. So I think this the viscosity of the water, of course, is one big issue that should be included there, and is included empirically, but not really. So yeah, that's a good question. I believe you are right. The environmental part is really important. It's not just.
So all of these test comparisons were done while CTD was in water.
Yeah, that's another source of uncertainty.
So the platform wasn't moving. Most of the time, XPTs are dropped while the ship's moving.
Yeah.
How's that going to impact the accuracy of both the fall rate and?
Yeah. So one of the things that when we deployed the XBTs, we are afraid that we saw that video that Francis showed that the XBT. So we are afraid that even going to the other side of the ship, if you drop an XBT and the CTD at the same time, maybe the XBT, one of them could go across the ship and hit it. So this was one of the concerns. So we generally drop before the.
You're still not underway. You're on stage.
No, it is. I believe it's underway. So Greg was one. Greg was one that deployed in the period.
To work up to ship speeds of 20 knots. Francis did some experiments not long time ago at different speeds, and it doesn't appear to be a big difference in the profiles of XPTs that you deploy at 10 or 20 knots. Still, we didn't do it. We didn't do the difference between no motion and 10 knots. But XPTs are not designed to be deployed where the ship is.
Sure, it's spools not only from the XPT but also from the canister.
Yeah.
So you're not dragging the XPT as you're moving. So theoretically, it's just very good quality.
But the difference between profiles of XPTs deployed when the ship is 10 or 20 knots is almost nothing. It's within the earth. That's the only thing with respect to velocity that we can see.
Yeah. Yeah, but you see that the CTDs themselves, when the up and down of the CTD, you have a big bias. So some people, they deployed, when they put the CTD in the water, for example, for 100 meters, and then they deployed the XPT both at the same time. We just didn't want to have a chance to. Yeah, so it was generally like 10 to 20 minutes before the CTD profile. Yeah.
Marlos, can you tell us or make any hypothesis or anything about implications on the computations of currents, transport, sea content, anything? Hypothesis. Once, suppose you have your enhanced probe that is working and you start using it.
Right.
How will those estimates of the different parameters that you compute with XPTs will change or be improved? Will they be improved?
Yeah, for the temperature offset, that has a smaller effect in the water than the depth offset, and it may affect the heat content, and I don't believe it would affect like currents, ocean currents, anything, because
The transport, you mean?
yeah, the transport, yeah, or the geostrophic calculation of the currents, because of that, it's just a bias, but you still have the difference between the two stations, so that that may be in the error of the method itself. I don't think that and that's what we showed in our 2013 paper, the other one with the AX8, that didn't do much different. So the depth error, it has been shown that is what people pursue the most. So we can't. I think the only way is with the pressure switches, and that.
So correct the depth.
Yeah. So.
And the temperature, with improved temperature sensor, will you get better XPT profiles that will have any positive impact on computing meridiomatic transport or ocean currents?
Yeah, I believe so. Yeah.
You will?
Yeah, I haven't estimated. No, maybe I had estimated that in our 2015 paper. When the effect is much smaller. Is, for example, a mock is maybe 0.1 is variable or something is
So
really small.
At the end, I'm thinking there is a point where you see if you want to continue with this work, because will it be worth continue if you don't see that the impact on the final parameters that you compute are negligible.
Maybe
Right.
I summarize your question. If you want to sell me this probe, how will you convince me that it's worth to buy?
You will get better results.
Here we just tackle mostly the temperature bias, right? So this is important, I believe, like for maybe the detection of for example, mixed layer depth, but this is something that need to be investigated more deeply. So I don't have on the top of my head what would be exactly the impact of an ocean current. But any bias that we can correct is better, especially this would increase very time the cost. Is just they would do the production. So the pressure switch is a different story. That would the price that we are like predicting would like double the probe the price. But these are very little. So if we can improve from 0.1, 0.12 to 0.02, so the better we have. So for each application may have a different sensitivity, even for the ones we have currently may not even be that much. But if they don't increase too much the cost and improve the accuracy, why not, right? I think that's the idea. All right, thank you. Ooh. Oh.